Hello, hello. Hey everyone, I'm Bowen from Near, and today I'm going to talk about a very exciting topic, sharded smart contract. Well, before diving into what that thing actually is, let's first review what sharding is. Hopefully by this point everyone knows about sharding, but just in case you don't, let's quickly kind of talk about what it is. So basically, it's a technique to scale blockchains. In a non-sharded blockchain, like Bitcoin or Ethereum mainnet and many others, what people do is that there are a whole bunch of nodes, could be 1,000 of them, but they all do the same thing. They all process the same transactions, do the same state transition, and agree on the same result. That, if you think about it, that's kind of inefficient. Because every node, by having more nodes in the network, it's not actually improving the performance of the network. So sharding is the idea that, well, let's do something else, which is that we have the network being divided into different shards. So each shard, you can think of as kind of like its own blockchain. Inside each shard, every node who validates that shard does process the same transaction, validate the same state transition, and agree on the same state root. But between different shards, they're doing completely different things. They have different state, they process different transactions, and so on. Essentially, the entire network is being parallelized by the number of shards, and kind of the more shards you have, the higher throughput the network has as a whole. So let's take a closer look at how it kind of actually works. I'll briefly describe some things about what Near has built for sharding. So in the traditional sharding design, usually each shard has its own blockchain called shard chain, and there is some beacon chain or main chain, whatever you call it, that orchestrates different things between shards. For example, assigning validators to shards, making sure that the cross-shard transaction is valid, and all of that. But there's a problem, which is that if each shard has their own blockchain, it's actually very complex, because on each shard you can have your own fork. What happens if when you send a transaction from shard A to shard B, it actually goes from a fork on shard A to a fork on shard B, and what happens if one of those forks gets rolled back later? That becomes very nasty. So in Near's nightshade design, we actually simplified things. We basically just say that there's only one chain. This chain, each block on this chain contains chunks, which are shard blocks from every shard. So there's no actual shard chain, even though logically you can kind of build this shard chain from this main chain. And this simplification makes a lot of things easier, and also not only easier to implement, but easier to reason about the security and so on. So brief high-level overview. So feature is that it has only one chain, and each shard doesn't need to have maintain its own shard chain. The execution is asynchronous because in order for cross-shard transactions to work, how it works is that it first gets executed on the shard where the transaction originates, and then receipts get spawned and sent to the destination shard to execute. And the security relies on serious validation. That's a new thing we launched last year. So what the problems that sharding trying to solve, I think, is mainly twofold. One is this scalability problem that I talked about earlier, which is that, well, you kind of want the throughput of the network to be high, here in a sharded blockchain design, the throughput should roughly scale linearly with the number of shards. So kind of more shards you have, more throughput you have. That's a great way to improve the performance of the network. But I think one thing that is not being talked much about is that it's actually a very effective solution to the state growth problem. Because in a non-sharded blockchain, you not only have the throughput problem, you also have the problem that the state is growing potentially very fast in cases of chains like Solana. And you need a way to address this problem. Otherwise, at some point, the state of the blockchain would be so big that it's infeasible for the nodes of the blockchain to hold the state. And that becomes a problem for the sustainability of the blockchain. So that's why people talk a lot about how you address the state growth problem. But for sharding, you can think of it as a natural solution to that because it essentially just divides the state into the state of the shards so that when you have more shards, each shard doesn't need to have that much state. So it also addresses that problem. But there is often overlooked detail that actually make it more complex, which is that while sharding does address both of the problem, there's an interesting corner case and a very important one as well, which is that a smart contract itself can grow very, very large. So if you think about the popular DeFi contracts, the likes of Uniswap or on Near, there are those consumer-based apps like Kaiching or Hot that have like millions or tens of millions of users. And when the state of all of those users are stored in the same contract, it just gets very large. And not only that, the throughput of the smart contract is actually limited by the throughput of the shard, meaning that even though you can have many shards, this smart contract, this very large smart contract, will have to live on a specific shard. And because it lives on a specific shard, the throughput is naturally limited by the throughput of a single shard. So it doesn't really benefit from the overall sharding design. Okay, so how do we address that problem? The solution is what we call sharded smart contract. What does it mean? It means that the smart contract essentially simultaneously exists on all shards. The contract code is global, it's available on every shard, and instead of storing the user account, user data on the smart contract account, it actually stores under the user account on each shard. So in this way, it scales linearly with number of shards and actually leverage the power of sharding. So let's take a look at some concrete example. So let's say you have USDT contract is a simple fungible token smart contract, and you have Alice and Bob who both have account registered on the USDT smart contract. So today what you do is if you want to send a USDT between them is Alice calls FT transfer and having Bob as recipient, and there's like sending one USDT, but this entire call happens on USDT.near. The execution all happens within the same smart contract. Now, what if we make it sharded? Now it's actually more interesting because it's no longer happening. The execution no longer happening on the USDT.near account. What's actually happening is that on Alice account there is a USDT.near namespace. It's kind of like this sub account in a sense of the Alice.near account. And it stores all the relevant data that Alice.near has on USDT.near. And similarly, the same holds for Bob. And if Alice wants to send Bob some USDT, what actually happens is that this Alice.near slash USDT.near, this entire complex namespace calls the namespace on Bob's account and says how much token you want to transfer. And when it gets executed on Alice's account, the number is deducted, and then when the receipts get executed on Bob's account, it's incremented there. As you can see in this whole process, the USDT.near account is actually not touched. So this is almost the same as if you do native token transfer between Alice's account and Bob's account, because they can live on different shards, and it doesn't have to be Alice Bob, and it could be like millions of users doing the same thing. So it fully takes advantage of what sharding allows you to do. Okay, that sounds cool, but how does it actually work? So there are two main technical components of the sharded smart contract design. One is what we call global contract code, and two is this ability to store data under user accounts rather than the smart contract account. So what does global contract code actually mean? It means that it's basically a special transaction that instead of deploying this contract code on some specific account, let's say Alice.near, it actually deploys into this kind of global state that is simultaneously available on our shards. So roughly how this works is that when you do this deploy contract transaction, it generates receipt that goes to every single shard. And on every single shard, the validators maintain this state for the global contract code, and the state root is being updated when it sees a new contract code being propagated to the shard. So it validates that so every single shard validates the state transition of the global contract state and update the state root there. The important thing to note here is that this special thing only stores global contract code. It's not a general purpose storage because that's very complex and also opens up a whole can of worms. So we basically limit this to only store contract code. And another thing about it is that this operation is very expensive because you need to have it simultaneously available on all shards, and essentially you burn a whole bunch of token to do that, meaning that you cannot just spam this to attack the network, and making sure that people only do this when there is actually need for it. So for example, if let's say Alice.near wants to deploy a global contract for multisig, and Bob.near see that, okay, now there is a multisig contract deployed, and he might also want to have multisig on his account because that's convenient. So what he can do is that instead of deploying another multisig contract, which is expensive, you can just say like, okay, I want to refer to this contract deployed by Alice.near, either by the account name, Alice.near, or by the contract hash. And essentially, this is a pointer to some piece of the state. So this operation is very cheap. And as you can see, this global contract code is already a very useful feature by itself. But in the context of sharded smart contract, it's actually a prerequisite because sharded smart contract necessarily has to have the code available on all shards. Okay, now let's talk about the second piece. How do you make sure that we can actually store user account, store data on user account rather than on contract account? So generally, the idea is that if you have a pretty expensive contract, whether meaning that you have a lot of users or you have a lot of transactions hitting the contract, it's usually because you store some information per user. If you don't do that, if you just store some kind of static information or something that's not kind of stored per user, then generally there's no need for a contract to be sharded. But let's say you do, and it's either like large DeFi applications or some consumer application that stores maybe a lot of information per user. So generally, the abstraction is that you have this mapping of user account ID to some kind of data. The data is obviously contract specific. What you do today is that the data is actually stored under the smart contract account rather than on the user account. Okay, so let's look at this example. So let's say you have the USDT smart contract. On the left-hand side, it's a single smart contract. It's basically like this giant table that stores mapping of account ID to balance, right? So, for example, Alice has 1 USDT, Bob has 10 USDT, Carol has 50 USDT. Now, what it means to store on the user account is that it's kind of like the inverse of that. The USDT smart contract, the USDT account itself doesn't store much information, and all the balance information is stored under this namespace that I talked about before. So, for example, on Alice.near, there is this namespace, Alice.near/USDT.near, and inside that namespace storage, it has some kind of key says it's balance, and it actually stores the balance under the key. And same for Bob and Carol. And as you can see, now we essentially changed the storage paradigm from having everything stored on the contract account to now actually everything stored on the user account. And as we know, sharding already deals with the kind of handling of the states of the user account, meaning that it is actually sharded based on some boundary. So like you have all the user account in this in the state namespace in the state state tree, and then you basically shard based on some kind of boundary that's determined by some specific account. So you already get that. Now, essentially what you get is that you also have this contract storage sharded just based on how sharding works, and you automatically get that. And if you have this contract that's very large, let's say USDT.near has 100 million users, you still have that account USDT.near with very small amount of storage, and then the meat of the storage is now on individual user accounts. So essentially, you transform the problem of like one account having a lot of storage to lots of different accounts, each having their own small piece of storage for this contract. And this would scale with number of shards. So this is a very interesting change, and obviously there's a lot of complexity behind things on how it actually works, how to handle the runtime, and so on, that we won't dive into today. But it suffices to say that this is a solution that actually addressed one of the big bottlenecks of the sharding design that people have today, which is that, what if you have a very large smart contract? It actually allows to shard the smart contract and have both scalable throughput for the smart contract and also manage the state size effectively. And with this design, makes sharding a very complete solution to the blockchain scaling problem, both in terms of the throughput, but also in terms of the state size growth problem. And we're building this solution at Near today. The first part of the components are already done, so we already have global contract code that is going to be released very soon. And now we're working on the second part, which is to allow smart contracts to store data on user account. So that's it. Thanks.